Okay, so today we're going to look at section 8.3, infinite series. In particular, we're going to look at a type of series that shows up all the time, and these things are called geometric series. So a geometric series is a series, it's a special type of series. So remember that in general we're looking at something like this. Sum of an, where n goes maybe from 0 to infinity, maybe it's 1 to infinity, it doesn't matter. We're looking at a series. So this an is the nth term, or a term given by a particular value for n. For a geometric series, what we're actually worried about is a series that does something like this. Let's notice that what happens each time. I start at some value. How do I move from one value to the next? Well, I divide by 2. I multiply by 1/2. As I go from here to here, I multiply by 1/2. As I go from here to here, I multiply by 1/2. And so on and so on and so on. So this is a geometric series. Geometric series is where we start at some value, and then each next term in the total sum is obtained by multiplying the previous term by some fixed value. And this is always the same as we move all the way down the line. So, for another example, there's another geometric series. Notice that's what's happening. I started a single value. Now, when I multiply by the negative 1/3. And then I multiply by negative 1/3. And so on and so on and so on. So when we have such a series, a geometric series that's special like this, I can write this thing in the summation notation in a very specific way. So let's look at what happens. So I'm going to write this as a times r to the n, where n goes from 0 to infinity. And in this case, what is that? All right, so let's start plugging some things in. When I plug n equals 0 in, I get a times r to the 0, but r to the 0 is 1, so that's just a. And then the next will be a times r to the first, ar squared, and so on and so on and so on. So notice what we've got. If we have a geometric series that behaves like this, then the very first value is a. And then how do I go from a to a times r? Well, I multiply by r. And then I multiply by r. And then I multiply by r. So the first value is a, and then what we multiply by is r. So this one I can write as sum of 1 times negative 1/3 raised to the n, where n goes from 0 to infinity. We may see that written in a slightly different way. This may be written as negative 1 to the n, if I put this to the nth power on the negative, and then 1/3 to the n as well. But this way is where we see the a value and we see the r value. Okay, now, that said, we should be able to notice a few things. Right? So the first question might be, does that sum even actually converge? Does it get closer and closer and closer to something? Let's notice for that first one that we started with, or I'll make an adjusted version. Suppose that I have 1/2 plus 1/4 plus 1/8 plus forever on out. So that's sum. The a value in this case is 1/2, the very first term, and the r value is what it takes to go each step, which is 1/2. Okay, so that's what we got, and I can ask, does this converge? Does this total sum actually sum to a value, a finite value? Or does it diverge? Does it get bigger and bigger and bigger and go forever? Well, this one we can actually think about. So think about it like this, right? So 1/2, suppose that I was 1 meter away from the wall, and I move 1/2 of a meter towards the wall. So this is half the distance to the wall. This next one is half of 1/2, because we multiplied by 1/2. So this is half of the remaining distance. Each time we multiply by 1/2, so each time we've covered half of the remaining distance. So this whole thing had better actually sum to 1. And we'll discover that it does. In fact, we'll discover that every geometric series converges as long as these things are getting smaller and smaller and smaller and not bigger and bigger and bigger. And in order to get that, what we'd like to do is we'd like to find a formula for the sum of a times r to the n, where n goes from 0 to infinity. So that's what I want to do. I want to come up with some way of figuring out what this is and saying, what does that series converge to, if it converges at all. And so we're going to do that. I'm going to develop this. It's in the text too, but I'm going to work through it as well. There's a couple of tricky, clever things that happen. But so here's what we're looking at. So suppose that I let Sn be the sum of all of the first n terms. The nth partial sum, which is the sum of the first n terms. But since the first term corresponds to n equals 0, that's actually n equals 0 to, well, so we're really going from 0 just to n minus 1. Let me write it out more like this. So this is actually a plus ar plus ar squared plus all the way out to ar to the n minus 1. Because this is actually n terms, because this corresponds to n equals 0. So this is Sn. All right, so now we're going to be a little bit clever. Right? And so we're going to be clever, and we're going to take Sn and we're going to multiply by r. So that r times Sn is r times a. Actually, let me write it like this. Ar. If I multiply this term by r, I get ar squared, ar cubed, all the way to ar to the n. So we got Sn, and we got r times Sn. What I'm actually going to do is subtract. What is Sn minus rsn? I'm going to subtract these two terms. Notice that if I subtract, ar minus ar goes away. Ar squared minus ar squared goes away. A never goes away because there's nothing here for it to cancel with. None of these things are a. So a is left when I subtract. These things are all gone. Even ar to the n minus 1 is gone because it's hiding in my dots. But this thing isn't gone either. The only thing that's left is the very first and the very last term. So we get, but since we're subtracting, this is now minus ar to the n. So that means that Sn minus rsn is a minus ar to the n. Which tells me that if I factor out Sn and I factor out a, then I can solve for Sn. And what we have is a formula for the nth partial sum. And that's nice because I don't actually have to sum up. If I wanted the 100th partial sum, I wouldn't have to sum up 100 terms. I can actually just put 100 in for n and get a value. And we'll come back and use this, but we're going to go one more step. remember that the total sum from 0 to infinity of any series is the limit of, as n goes to infinity, of the nth partial sums. So I take the partial sum, and then I take a limit as I add more and more terms into these things. So I'm taking the limit as n goes to infinity of this whole piece. But as n goes to infinity, the only piece that has an n is this r to the n. So what happens as n goes to infinity to r to the n? Well, we have to be careful. If r is something like 1/2, say, so if the ratio, the multiplication term as we go from one term to the next is 1/2, then when I take it to bigger and bigger powers, it gets smaller and smaller and smaller, and actually goes away all the way to 0. And we get 1 minus 0 over 1 minus r, as long as this number here is less than 1, so that bigger and bigger powers make it go smaller and smaller and smaller. And so we end up with a over 1 minus r. As long as, really, it's actually the absolute value of r is less than 1. This means that r is between minus 1 and 1. I'm allowed to have a negative r value. If it's negative 1/2, bigger and bigger powers still go down to 0 as well. Okay, so we get this formula as well. And so let's apply that to a few examples. Let's calculate this first. So this is sum a r to the n equals 0 to infinity, where a is 1, the first term, and r is the multiplication term, which is minus 1/3. So that this sum, according to the formula that we just came up with, is a over 1 minus r, which is 1 over 1 minus, don't forget your minus signs, minus 1/3, which is 1 over 1 plus 1/3, which is 4/3. So I end up getting 3/4. Let's calculate the sum from n equals 4 to infinity of 2 times 0.3 to the n. All right, let's notice something. If I started to write this out, then the very first term would be 2 times 0.3 to the 4th power. The next term would be 2 times 0.3 to the 5th power, because now n is going up. The next term is 2 times 0.3 to the 6th power, and so on and so on and so on. So in fact, this is a geometric series, where this entire piece is the first term, which is a, and each further step I get by multiplying by a 0.3. So r is 0.3. Which means that the sum of a over 1 minus r is 2 times 0.3 to the 4th divided by 1 minus 0.3. All right, so when we don't start at 0, the easiest thing to do is to write out the first few terms, notice what the first one is, and notice what the r value is. There are other ways that you could think about this, but this is the easiest approach. let's calculate the sum from n equals 0 to 100 of 6 times 1/3 to the n. Now, let's be careful. When I say n equals 0 to 100, I'm actually including 101 terms. So this is actually S sub 101. And that's actually what we're asked to calculate here, because this includes 101 terms. And so in that case, now we need to go back and look at our formula. S sub n was a times 1 minus r to the n all over 1 minus r. But n in this case is 101, so this is a times 1 minus r, which is a third, to the 101, divided by 1 minus 1/3. And a, careful, a is 6. The first term, because when I plug 0 in, this becomes 1. Okay, let's look at one more. Drug dosage in a body. So what we're going to do is many drugs that are administered in hospitals or from pills that you take on a daily basis, many of them decay according to an exponential decay model. That is, at the end of the day, after 24 hours, there's not a fixed amount left, but generally speaking, there's a percentage of what your initial amount that was in the body. There's a percentage of that remains in the body. Right? So for instance, suppose that if we have a drug dosage of 300 milligrams each day, and after 24 hours, we have only 22% remains. 22% of what's in the body. Okay, so this is an exponential decay model where no matter how much you start with, whatever's in there at the beginning of the day, by the end of the day, 22% is left. And so what that means is, after day 1, there's 22% that's left, but then that still is going to decay according to 22% by the end of day 2. So those leftover stuff after day 1, it doesn't all disappear ever. After day 2, there's still only 22% of that left. So so we have 300 milligrams, and 22% remains after 1 day. So we are going to then take a new pill every day. So let's let Q sub n, so Q sub n will be the amount in the body right after we take the nth pill. So the Q1 is 300. That's how much we started with. All right? So what happens after we take the second pill? Well, we take the second pill at the end of 24 hours. So we have 22% of the 300 that we started with. So we have 22% of the 300 that we started with, but then we have another 300 milligram pill that we take. So this is 300 plus 300 times 0.22. This is how much is left right after the second pill. How much is left right after we take the third pill? Well, we have 22% of what was left at the beginning of that session, and then we add another 300. So we have our new dosage, and then we have 22% of the amount that was left right after we took the second pill, which is 300 plus, well, if I put that 22 onto each of these pieces, I have 300 times 0.22 plus 300 times 0.22 squared. Okay, and now it shouldn't be too hard to see what's happening. as we move down, if I would go all the way down, what is Qn? Well, if each time that I do this, I'm going to add another 22% all the way through, and then add another 300 at the beginning. So it's going to be 300 plus 300 times 0.22 plus 3, and then we're going to have all this at the very end. But notice one thing, after the third dose, this was only a 2, so this is really going to be 0.22 to the n minus 1. So our real question, is, what happens in the long run? So what is Q infinity? If I would take an infinite amount of doses, how much of this drug remains in my body? This is an important question because there are some medicines that you are on for the rest of your life, which means that you may have a drug buildup in your body, and you need to make sure as a doctor or a pharmacist or a nurse that buildup doesn't go beyond a therapeutic level. So we want to know what happens in the long term, Q infinity. Right, so this should be a sum as this goes all the way out. 300, and what is that? 300 times 0.22. So the first term is 300, and the R value as I move is 0.22. So this is 300 times 0.22 to the n, where n starts at 0 and goes to infinity. Because when I plug 0 in for n, the first thing that I get is 300, and then the next terms that I get add a 0.22 each step on the way. So this is the long-term, the long-run dosage of the drug, that it remains in the body. But I know what to do with this. This is a geometric series with A equals 300 and R equals 0.22. And just so we can get a good idea of what that is, this works out to be 384.6. So even though at the end of each day we have a little bit more because of all the buildup from all the previous days' amounts of dosages, by the time we're done, even after an infinite amount of doses, we only have 384.6 milligrams, which means as long as this is not above a therapeutic level, and as long as this is not a dangerous amount, that initial 300 milligram dosage is a safe dosage. Okay, and that's what we got for 8.3. I'll see you next time.